Music theory, the harmonic series. Remember, our primary objective here is to learn music theory in a practical, applicable manner, one which helps us actually play our instrument. In our case, our instrument primarily being the guitar. However, the same concepts do apply to other instruments as well. In particular, we would like to learn the overarching concepts that are scalable as opposed to learning rules that are only applicable to a certain area of music, which actually then cause hurdles that we have to overcome when we are expanding our knowledge. In other words, we are attempting to learn it correctly from the start so we don't have to unlearn, but then rather can expand freely with our knowledge. To do that, we want some fundamental understanding of, in essence, the science behind sound and the pitches and what's actually happening mechanically, physically, when we interact with our instrument, when the noise from the instrument interacts with us. Last time, we had a general idea of what basically sound is, and we thought that, and we saw that, you basically need three things. You need something that the sound is coming from, such as in our case, a string. You need a medium that it's going to travel through that we can visualize, typically as water. Comparing it to a pebble falling in water, we see ripples coming from it. In our case with sound, the medium is the air if we're in a space with an atmosphere, not in space. And then it needs a receiver, which typically is going to be the ear. That helped us to understand a little bit about some of the things that we take a priori just as is when we learn just the guitar in general, that being the notes of the guitar, which are just assigned to us, but now we see that they're actually coming from a measurable quantitative component, which helps us to understand why there are patterns that are happening when we start to list out the notes, and we understand kind of the linear nature of the notes, meaning they're kind of like a numbering system that can go up to infinity, as well as the circular nature, because we got a little bit deeper understanding of the octaves and how they work, and how therefore to properly visualize the notes, it wouldn't be a circle, it wouldn't be a line, it would be a spiraling kind of thing that has both linear increases and decreases in an infinite way, as well as repetitive areas. But we can't, as human beings, visualize that properly. No one can. It's not just me. It's not just you. We're not stupid. No, it's too complex to visualize things like that. Therefore, we're going to pick the task that we are doing and visualize it as either a line, a linear progression that goes out into infinity, or as a circle like a clock. And that will help us to achieve the task that we want to do musically, typically. Now, the other thing that we haven't touched on that we just kind of accept a priori when we do our mapping out of our music theory is the progression of the major scale and the related modes that it's built off of, which we just say is the formula. We have our 12 notes and we say there's a whole half, whole half, which we'll get into more later. But that is something that we're just going to accept. That's just the way it is. But we want to then dig a little bit deeper here and think about maybe why that is the way it is, as well as why different instruments sound different. And that's basically what we will get into here. Remembering that there's nothing wrong oftentimes when learning something to accept certain conditions a priori, meaning they're going to say that the music teacher says that's the formula, so that's the formula. I'm just going to apply out the formula. And I'm going to trust the system that there's some reason that they came up with that. But obviously at some point in time, we might want to question that or dive deeper into why did that come about. And that's appropriate to do as well, because that could lead you to different ideas on what you want to do with music later. So don't let the fact that you just accepted something because that's the way it happened traditionally stop you from at some point saying, well, why is that the way it happened? You don't need to question everything from the start, because that's going to take forever. You're going to try to rebuild everything from the start and question everything to a strong degree. But you do want to keep open the fact that I would like to know more about the things that I've accepted a priori in order to build on it from there. Okay, so the harmonic series. The harmonic series is a naturally occurring sequence of pitches produced when a single note called the fundamental vibrates. So we're going to imagine the noise is happening. It's coming from, we're going to imagine a guitar, the string of the guitar is plucking. We compare that to a rock that's dropping into a puddle of water. We note that when a rock drops into a puddle of water, we see waves. The waves we can often imagine as a sine wave, but in reality, we can imagine something more like a puddle of water. It's actually a wave that's going all the way around the puddle, right? It's emanating from that source to wherever it's not being blocked from emanating from that source. And it also doesn't have just one wave. It actually has one primary wave. You're going to say there's the big wave that's happening. That's the one I want to catch if I'm surfing out there, unless it's too big. But then it also has the littler waves that are going to be taking place. And so that's the nuance that we want to basically keep in mind here, the nuance of the littler waves that are happening. So when we recreate the noise, then electrically, it used to be that they weren't really good at taking all the harmonics, all the littler waves, because it gets somewhat complex and they differ on different instruments, although there's some symmetry or some consistency to it, as we will see. And that's why things used to sound more digital, and that's why AI has gotten a lot better at predicting these types of harmonics based on different instruments. All right, so it forms the physical and mathematical fundamental for pitch, tone, and tuning in Western music. So basically, we can think a lot of the things that we came up with in Western music, such as scales and whatnot, may be derived in part, at least, from this pattern. Basic concept. When you play a note, say on a string or in a tube, so stringed instruments versus tube instruments, say wind instruments, right? You don't hear just one frequency, you hear the fundamental, meaning the big frequency, the one that we use to name the frequency, but that's the lowest pitch, a series of overtones. So that lowest pitch, like in music, when you hear that driving bass beat, the lowest note, right, is going to be the one that's really driving home in whatever sound is happening. That's the biggest wave when you drop the rock into the puddle or put the string to a task. But you have other tones that are coming off it as well, a series of overtones, which are higher frequencies. These overtones are called harmonics. So each overtone is a whole number, a multiple of the fundamental frequency. So that's kind of interesting. I don't want to get too in the weeds on the math on it, but I just want to point out here that there's variation because it's a whole number multiple, meaning it's not like a fraction multiple typically, right? It's a whole number multiple, but there's still variations that you can imagine that you would see happening. So that means that if you're trying to recreate something, then it's not like you have an infinite amount of variation of the overtone. There's some predictability. So if you were trying to create like an AI simulation of a guitar string, then you can imagine what would you have to do? Well, you would have the fundamental. That's pretty easy to tie down. But then you have to layer on top of it the simulation of all the other ripples. How would you do that? Well, it's not like there's an infinite number of them because there's some restriction to the way the pattern's going to work generally, right? So let's look at it here. So a series of numbers and frequencies. So here's the harmonic, the first, the second, the third harmonics that we're talking about. Here's the ratio 1 to 1, 2 to 1. So they're whole number ratios, 3 to 1. Notice this one approximate, so not perfect all the time, possibly. Then the musical intervals. Now we haven't dived in a lot to the musical intervals yet, but these are just kind of distances you can imagine. And we typically, when we get to our music theory stuff, are going to measure those differences and give them a name, the unison being the same note, so we haven't traveled anywhere. And then an octave, usually 12 notes up, right? That's going to be when it repeats. The perfect fifth is going to be one that's going to be in most of the scales, except for like the Locrian with the modes, the double octave, and then the major third, and then the major third. So notice when we have, say, a scale, let's imagine it's a C major scale. Remember, one of the things that we generally just accept when learning to play an instrument is the formula that is applied to pick certain notes out of the 12 notes in the musical alphabet to create a scale, which we're actually going to be playing within. In future presentations, we'll talk a lot about applying the formula to create different scales and how we can compare those different scales, how they're related, and how they can be useful for actually playing things. However, at this point, we want to get a general idea of the question that will typically come up if a music instructor says, hey, look, we're just going to apply this formula out. And that's going to be, well, where did you come up with the formula? Noting that sometimes it's useful to just simply accept things a priori. If the music teacher says, hey, this is the formula that we use because that's what they came up with, we've been using it forever, it works great, then we're going to say, great, let's just learn from there and we're going to be moving forward from that point. But just because we're going to move forward and accept that, even if we believe that that's true based on tradition, doesn't stop us from wanting at some point possibly to ask the question, why was that the way it is? And even if we don't think it's going to change our opinion, looking into it can give us a better understanding about certain things that could give us some musical ideas on how we want to apply our music and go on our musical journey going forward. So at this point, I just want to give a little bit of insight on the things that might have gone into basically generating the formula. The other thing I think is really useful here also is that particularly where I am at, sometimes people are kind of down on Western culture and they have this cultural relativism kind of thing. And so if that's the case for you, you're going to tend to say possibly, well, that must have been just a cultural kind of thing of Western culture, and I should be able to play any notes that I want to play and so on and so forth. And you can play any notes you want to play. But I just want to, if we see that this formula came about of something that's not specifically or completely out of a cultural context that might be useful to some people to understand, meaning if this is coming from something that naturally occurs in nature, it's not simply a cultural thing at that point, it's a human thing because all of our ears are picking up and tending to like similar kind of frequencies. So if that is the case, then it's an interesting project to look at different cultures and see if there's going to be similarities in the way music was constructed in different areas because of the similarities in our human experience, of sound would be the general idea. Now, you would expect some cultures, I think, have like pentatonic scales might be more common, meaning 5-note scales than a 7-note scale, for example. But even in Western music, we often play like 5 out of the 7 notes, and then we have the 7 notes added on. So, but I would assume that there's going to be similarities in different cultures because of something like this in terms of how the notes were created. However, there's 2 things that I think you might want to keep at least in the back of your mind that have a practical component as well to why we might have constructed the chords this way. One is that you've got your 12 notes. We know that those are going to be in linear fashion. They keep on going up forever. We also imagine them in a spiral as the octaves basically go up. If you pick any note, then you would expect that you're going to play something next to it. Usually you're going to play one that's going to skip a note. Why would skipping a note be the default thing to do? Because if you skip a note, it's going to sound like it's a stair step up. It's going up, but it's not too far that it sounds completely unrelated, and it's not too close that it sounds too muddy. That's going to be the general like intuitive thing that you would think, right? So whatever note I'm on, I'm going to skip every other note. Why? Because that's going to give me a nice stepping stone. It leads in, but it's not too close. Now, of course, we have 2 instances in our formula where there's these 2 notes right next to each other. That happens here, and when we go around back up to the top. So one reason you might expect that to be the case is because you want some variance. So if I'm taking all these steps, you would expect that you'd have mostly whole steps and a couple half steps maybe so that everything is not exactly uniform. That's one just kind of intuitive idea that you might come up with, which you can also see over here in a circular fashion. If I'm on C, you've got the whole step, the whole step, the half step, the whole step, the whole step, and then the half step. So the other thing that we would see is, maybe there's something with the harmonics that's going to be an idea of why it comes up. Now, to understand this a little bit more in depth, we need to understand the intervals. So we'll talk more about intervals later, but just to get a general idea, the intervals are just a measuring tool for how far away a note is. So if I go from this C to this E, it's 1, 2, 3, 4 steps away. So I'm going to name that interval by relative position, which is one of the things we're having issues with because that kind of forces us to think in a certain way. But if we're in the key of C, then you can see this is the third note in our key, but it's actually 4 steps away if I looked at the 12 notes in our system. So we call that a major third. If it was only 3 notes away, it would be a minor third. So in essence, all we're doing is we're taking every distance that is possible and we're giving it a name based on the relative position of the scale. And so that's what these are going to be. So if we looked at the major scale, our intervals are traditionally based on the major scale. Let's try to look at what happens in this natural occurring harmonic. So remember, I like to imagine a rock dropped into a pond. You've got one big wave that's going to be the main tone, similar to sound waves, and then you've got the other ripples. So those other ripples are multiples of whole numbers. So the unison is the one big wave, and then you've got an octave. So it has an octave. So that makes sense because now that would be like a bar chord, right? On a guitar where you have multiple repeating notes on it. So, okay, that's fine. And then you've got a fifth. Now the fifth is kind of interesting because if you look at our formula over here, the fifth is what we usually think of as like the stable note. Power chords, which are common in like rock and roll, are going to have the fifth. Now it's kind of interesting because it's not only in the C major that you have a fifth, but if you look at all the other modes, Dorian, Phrygian, Lydian, Mixolydian, Aeolian, all of the normal modes have a perfect fifth in it. So so it's a stable sound. So you would expect that would be included. I would think, I haven't looked at every other culture's, basically musical, how their music is put together, but you would expect there'd be a fifth a lot of times because it's so stable sounding in scales that would come up in different cultures. The only one that it's not in is the Locrian, which has a flat fifth, which is the weird mode. That's why it's weird, because it has a flat fifth and all the rest of them do not. There's an augmented fourth here, so there is that same, but it also has a fifth in it. But we'll get into that later. And then we have the double octave, so another octave. So now you've got these ripples that are repeating. The big ripple has the same octave as another little ripple and another little ripple. And then it has a major third. Now that's what you would kind of expect in Western music from a Western music standpoint, because of course the third is going to be the distance in a major scale from this note to this third note, which is actually a distance of 1, 2, 3, 4 half steps. So the third position is 4 notes away. It's a 4 note away major third is what I would call it. It not only happens in the Ionian mode, but when you play on other roots, the Lydian and the Mixolydian, which is the 1, 4, 5, the 3 major modes that you could build chords from, also have a major third in it. But then something interesting happens that this one has a minor third. So that's weird. The Harmonic series isn't just geared towards the major scale, because the defining factor between the major and the minor is the third. So now it also has a minor third to it, which is interesting because these set of notes that we came up with actually come up with 4 more of them actually have minor thirds than the major thirds, meaning the major minor scale, which is Aeolian, and the Dorian and the Phrygian all have minor thirds. Meaning if you counted from the A and you went from the A to the third, which would be a C, from here to here, it actually has a distance of 1, 2, 3, as opposed to a distance of 4 notes. So that means, and the Locrian has a minor third. So there's actually more minor thirds when you look at it from a modal standpoint than there are major thirds, although the major third is kind of the main one kind of. So then this one's funny too, because you've got a seventh here, and the seventh is a flat seventh, which once again isn't typically in the major scale. So you might say, well, that's weird. Why would the seventh be the one? Why wouldn't it be a major seventh, not a minor seventh? Because the major seventh is what would be on the major, and it's saying it's a flat seven. But it's kind of interesting because notice that only the Ionian and the Lydian have a major 7. The rest of them, when you're playing in Dorian, Phrygian, Mixolydian, Aeolian, and Locrian, all have flat 7s, right? So it's kind of funny that this series actually lines up to some extent more to the Mixolydian mode, you would think, right? Because it has a mixture of the major and minor, which is what we see in the blues oftentimes, and it has a flat 7. So that's kind of interesting. So I think that's kind of why the folksy music, I think historically there was a folksy kind of thing that was happening, which was mainly Mixolydian, that people liked the jamming in, the rhythm of and whatnot. And then we got into like the major scale because it's more storytelling based, right? It's more, it gives you more of a feel of the is directional possibly instead of just jamming kind of feel, I think possibly is the thing. And now, of course, we've kind of returned to some degree to a little bit of both, right? We've got this. So, but in any case, so it's interesting that between the major and Mixolydian, you would think that those would be the things that would kind of pop up in different cultures because those are because there's a reason that's human based, not cultural based, based on how sound works as to why you would think the culture would come up with things. All right, that's my general breakdown of it. So chord construction, and I'm not saying that's a perfect breakdown of it, by the way. I'm trying to give some general ideas as to why that thing that we're going to simply accept going forward may be the way it is. And if you want to dive deeper into that, then dive deeper into it. So triads and extended chords like seventh, ninths are built on the early harmonics. So tuning systems. So just intuition, just intonation is based on exact harmonic ratios. However, equal temperament slightly adjusts these to fit 12 equal divisions. So in other words, you've got this a little bit of an issue here because it didn't fit perfectly, and we liked in our human world, right? We like things to be symmetrical, and something didn't come out that was exactly symmetrical. And so then we wanted to make it symmetrical, which again is an interesting tweak that happened because that's a little bit slightly different than what's happening naturally, which might give you some ideas what you might want to do musically, because that could give you an idea to untweak it and say, well, this is going to sound more natural maybe if I did that versus artificially symmetric, which is what we human beings like to do. Take something, we're going to take trees and whatnot that are growing, there's vines growing out all over the place, and then we put them in a nice symmetrical line in front of our house because we like it in a straight line, right? So that the balance between symmetry and messiness is something to play with. So the timbre, the tone color, so the strength and presence of different harmonics determines how instruments sound unique. So notice that we have this series that's happening here, and there's a ratio that's happening, but the ratio is also always whole ratio. So you would think that still gives us variance that happens between different instruments, which is interesting because that's what's going to give us the different feel of different instruments, which again, you can imagine the big puddle with the big ripple coming from the rock, and then all the other ripples are going to be slightly different on the other instruments. And with a guitar in particular, that becomes something that you can do uniquely on the guitar. And that's something possibly that AI might still have a little bit of trouble doing. AI is getting quite good at simulating things that are quite complex because they're layering different sounds on each other to simulate the ripple that's basically happening. But it's going to be more difficult on certain types of instruments like a guitar, you would think, where you can manipulate the timbre all over the place, right? You can put hammer-ons, you can bend the chords, you can slide on the chords, you can put vibrato on the chords, you can use your right hand to pick the chord on different areas within the string, which is going to give it basically a different feel to it. You can use muting techniques. All of those things, although producing the same overtone, will likely produce a wide variation of timbre, even though it's coming from the same instrument. A little bit more difficult to do that on like a piano, for example, because although you have pedals and whatnot, and you got the force of how hard you hit the key, and that does give you a lot of variance. Not maybe quite as much though as, of course, a guitar, where you can do all this crazy stuff. You can actually move the guitar around. You can hold it to your body. You can put it away from your body. If you put electronics in there, then of course you're all over the place on these different variants that you can do, even though you have the same basic kind of overtone. So instrument design. So brass instruments use the harmonic series directly. String instruments use harmonic flageolet tones to divide strings into equal parts. So let's think about the guitar in more detail. So visual representation, imagine plucking a string on the guitar. So let's say we had this one long string on the guitar. You can kind of imagine in an analogous way as dropping the rock into the puddle. So it vibrates as a whole fundamental. So you can imagine the whole string, if you pluck it, vibrating. The whole string just going back and forth. That would be what we can imagine the fundamental. However, as that is happening, similar to multiple other ripples, it also vibrates in halves. So if we cut the string in half, if I plucked this whole thing and I wasn't holding down any frets, then you can also imagine like the middle of this thing is going to be split, and this side is going to be vibrating and this side is going to be vibrating opposite, like a sine wave to each other. So the whole thing is vibrating with one big vibration, and each side is vibrating opposite to each other, and in thirds. So the third harmonic, each division creates an overtone that stacks. So you can also imagine the string broken up into thirds. And you can imagine that those thirds are going to be vibrating opposite to each other. So similar to the rock that drops in a pond where you get one big ripple and multiple different ripples, when you're thinking about a string, analogous, the entire string is waving, one big ripple, and then you get smaller vibrations of the string as it is subtly broken into halves, vibrating separately, and into thirds, vibrating in thirds, which creates the different harmonics. Now, of course, if you were to put your finger up on the fretboard, what are you doing? You are, in essence, plucking a shorter string. That's all we're doing. So what's going to create the sound on the guitar? The length of the string and the thickness of the string is going to change the vibrations. So implications in ear training and composition, musicians learn to hear harmonics in tuning, orchestration, and improvisation, which is one of the things that's, again, crucial to the guitar. And I think that's really a cool thing with, in particular, the guitar, although to maybe a lesser extent, in my opinion, to other instruments as well, in the day of AI. Because I think one of the things that might happen in the day of AI is simple beats can be simulated. And you can use AI stuff to kind of create music and even complex things. But there's got to be some kind of consistency, you would think, with the AI. Whereas if you get into this more kind of weird jazzy stuff that's bending strings or doing more things that are not exactly uniform, that might be something of more interest. I don't know, I'm just guessing as time passes, as people look for things that are more human-based, even though the AI is able to master more things. So it's kind of interesting on where like music's going to go and art in general is going to go once the AI can mimic what we've basically done in the past, right? It's compiling together the stuff that we've made in the past and spitting it back out at us in cool different combinations. So now the question, so now in the future, what's that going to do to our artistic goals, right? So it'll be kind of interesting. So composers use knowledge of the harmonic series to create resonance, blend, and natural voicings.